Hello friends, welcome back to the lecture series on high voltage engineering. Today's topic for discussion is partial discharge measurement. This partial discharge measurement is basically done for the different insulating materials. Earlier, the testing of insulators and other equipment was based on the insulation resistance measurement. Like we used to measure the insulating resistance, then dissipation factor, that is loss factor, then breakdown test. So generally these kinds of tests are conducted on the insulators and other equipments. In further investigations, it was found that weak points in an insulation like voids, cracks, and other imperfections lead to internal discharge in the insulation. These imperfections, being small, were not revealed in capacitance measurement, but were revealed as a power loss components in contributing for an increase in dissipation factor. So when the capacitance measurement is generally done, these imperfections cannot be identified. So these imperfections can be identified only when there is a power loss component measurement. In modern terminology, these are designated as a partial discharge, which in course of time reduce the strength of insulation. It means slowly this partial discharge which takes place in the crack or in the void or in other imperfections may lead to the major breakdown. So the strength of insulation leading to a total or partial failure or breakdown of the insulation. If the sites of partial discharges can be located inside an equipment like in a power cable or a transformer, the region of greater stress and imperfections in the fabrications can be known. Electrical insulation with void, that is shown in figure. So you can see this particular figure where the insulation is shown. This insulation consists of a void. This particular figure we have already considered in previous lectures when we discussed the breakdown phenomenon due to gas pockets or imperfections. So this is that void which is present in the complete insulation. Now when there is a void present, that void acts as or offers the capacitance that is represented as CA. So consider a capacitor with a void inside the insulation. So CA can be called as the capacitance of the void. CA is called as capacitance of the void. The capacitance of the void is represented by a capacitor in series with the rest of the insulation capacitance, that is CB. So CB is the capacitance of the remaining series insulation. Capacitance of the remaining series insulation. remaining series insulation. So you can see that this is the insulating device. Particular diagram is showing the insulating device which has a void and its capacitance value is Ca. So when we have the Ca and Cb present, so that Ca and Cb are shown in the equivalent circuit diagram. It is shown in the equivalent circuit diagram. So we have Ca and Cb. As there is a space, void, cavity present, this is also called as cavity. Like a tooth cavity, similar way there is an insulating cavity. So this cavity basically gives a breakdown, spark formation, partial discharge, and hence it is represented with this particular gap of breakdown. The remaining void free material is represented by the capacitance Cc. So Cc be the capacitance of the remaining part of insulation. Capacitance of the remaining part of insulation. The remaining part of the insulation. So when the voltage across the capacitor is raised. So if I just consider this insulating medium and the voltage is applied between these 2 points. Between these 2 points. Let us say this is point A and point B. So as this voltage across point AB is increased, that is raised, a critical value is reached across the capacitor Ca. So this voltage called critical voltage across Ca occurs and a discharge occurs through the capacitor. That is, it becomes short circuited. So that short circuit, so I just consider a void, consider this void, and due to the application across the complete specimen or complete insulating medium, a discharge due to the breakdown takes place. And that breakdown bridges the gap between the 2 points or between the surfaces of the void. So this is void whose capacitance is Ca, and due to the application and increase in voltage, say VAB, the voltage across the Ca, that is capacitance Ca, called critical voltage. This is called critical voltage reaches, and therefore a partial discharge takes place. That is, it becomes short circuited. And this is represented by the closure of the switch. So you can see this is represented by the closure of the switch in equivalent circuit. Now, the terms which we have used, like a electrical discharge. So what is electrical discharge? The movement of electrical charges through an insulating medium. So this is nothing but the movement of the electrical charges. Electrical charges. And therefore it is referred as the electrical discharge. The process of this electrical discharge or the post breakdown phenomenon is already learned in the previous lecture series on unit number 1. Another point of discussion or the terminology is partial discharge. So the partial discharge which is given, the name of this particular topic, partial discharge, that is it means that an electrical discharge that only partially bridges the dielectric medium. So this is a partial breach. only for small time period. So this bridges the gap between the 2 points or between the surfaces of the void. So that is called as a partial discharge. Internal discharge are the discharges in cavities or voids which lie inside the volume of the dielectric. So this is also called as internal discharge. So hope you understood the concept with this. Now let us understand the circuit arrangement for detecting the partial discharge. The figure shows a straight discharge detection circuit. Now, in this case, the high voltage transformer shown. So this is high voltage transformer, which is named or numbered as 1. So I can say number 1 is HV transformer. HV transformer. A resonant filter is used. So point number 2 is filter. The purpose of this particular filter is to prevent any pulses starting from the capacitance of the windings and bushings of transformer. So basically that avoids or acts as a filter to filter out the waves. That filters the waves which are generated due to the capacitance of winding and the bushings of the transformer. Now, CX is the test object. So I just named this CX here so that you can understand. CX is test object. The object, the sample which we have to be tested, it is placed here. Then CC is the coupling capacitor. CC is coupling capacitor. ZM is detection impedance. Detection impedance. The signal developed across that detection impedance is passed through a band pass filter and amplifier. So point 3 is band pass filter. So whatever the signal is developed here in detection impedance that passes through this band pass filter, that is point number 3. And amplifier, that is point number 4. Amplifier, that is point number 4. And it displays on a CRO. So point number 5 is CRO. So this particular figure that is straight discharge detection unit has point number 1 as high voltage transformer, 2 with a filter, 3 with a band pass filter, 4 with the amplifier, and 5 is CRO, nothing but the display unit. Then we have VK, CK, and QK. These are terms VK, CK, and QK with the calibrating pulse, calibrating pulse. So that calibrating pulse is Vk. Calibrating capacitor, that is Ck. And calibrating charge, that is Qk. Charge we know, pulse means a voltage pulse, that is V, capacitor means C, and charge means Q. The only with the abbreviation K, it indicates calibrating. Only indicates calibrating. So in this figure, whatever the discharge pattern displayed on CRO screen of a partial discharge detector with an elliptical display is shown. The sinusoidal voltage and the corresponding ellipse pattern of the discharge is shown in the next figure. So you can see this where a sine wave, that is sinusoidal wave, and the elliptical display sweep display is shown on the CR screen. The sinusoidal voltage and this ellipse pattern, which is shown, had and a single corona pulse in a point plane spark gap. So for point plane, so you can see this is your point plane. This is point plane. Another end is grounded. So this is your point plane. So the corona discharge in point plane configuration is again shown as a sample in figure B, in waveform B, and in waveform C. When voltage applied is greater than that of the critical inception voltage. Critical inception voltage, it means that the voltage at which discharge of specified magnitude occurs. Of specified magnitude occurs. So therefore, this critical voltage means when the voltage applied is greater than that critical inception voltage, multiple pulses appear, and that multiple pulses is shown in figure C. That is shown in figure C. A typical discharge pattern in cavities inside the insulation is shown in figure D. So you can see this is what the void pulses which are shown. So it's a negative pulse, and this one is the positive pulse. This pattern of discharge appears on the quadrants of the ellipse. On the quadrants of the ellipse. On the quadrant of the ellipse, which correspond to the test voltage rising from 0 to its maximum value. Either it is negative or positive. The discharge usually or generally start near the peaks of the test voltage. So when that voltage has increased and when that voltage is to its peak value, that discharge starts, but spread towards the zero value as the test voltage is increased beyond the inception level. The number and magnitude of discharges on both positive and negative cycles are approximately the same. So you can, if you just count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Then here 4, 8, 12. So almost same. Almost same. A typical discharge pattern from a void bounded on one side by the insulation and other side by the conductor is shown in this figure. So this is your another figure, that is discharges in voids, one side with the insulation, other side with the conductor. This pattern of discharge is common in insulated cable. In insulated cable, when the discharge is made up of a large number of pearls of small magnitude on the positive cycle and much smaller number of large magnitude pulses on negative half cycle. So again, for both negative and positive half cycles, it is shown on the ellipse. In the narrow band detection scheme, ZM is parallel LC circuit tuned to 500 kilohertz. So that ZM which we have already seen, shown, has a parallel LC circuit so that it can be tuned to 500 kilohertz frequency. The band pass filter has a bandwidth of about say 10 kilohertz, maybe plus minus, and the pulses after amplification get displayed in an elliptical time base of a CRO. In wide band detection, this is narrow band detection. In wide band detection, the ZM is RC network, whereas in narrow band detection, ZM is parallel LC circuit. So in wide band, ZM is RC network and connected to a double tuned transformer. The bandwidth is now 250 kilohertz with center frequency between 150 to 200 kilohertz. That displays the signals on CRO. With tuned narrow band, the discharge can be detected with sensitivity less than 1 picocoulomb for test piece capacitance of 100 picofarad. So with tuned narrow band detectors, the discharges can be detected with a sensitivity less than 1 picocoulomb for a test piece capacitance of 100 picofarad. So that's all with this partial discharge measurement, generally which takes place whenever we find the partial discharges in the voids, and that must be detected. So this particular test can detect that partial discharge in the cables, in the transformers, etc. So therefore, this particular test is very, very helpful. Hopefully, you understood this topic with the definition, circuit, and the corresponding waveforms. So thank you so much, guys. Take care.